Welcome to this presentation. This video is about look angle determination. The look angles for the ground station antenna are the azimuth angle and elevation angles which are required at the antenna so that it points directly at the satellite. The look angles were determined in the general case of an elliptical orbit, and that the angles had to change in order to track the satellite. With the geostationary orbit, the situation is much simpler because the satellite is stationary with respect to Earth. Although in general no tracking should be necessary with the large Earth stations used for commercial communications, the antenna beam width is narrow and a tracking mechanism is required. This tracking mechanism is required to compensate for the movement of the satellite about the nominal geostationary position. With the types of antennas used for home reception, the antenna beam width is quite broad and no tracking is necessary. And this allows the antenna to be fixed in a position as evidenced by the small antennas used for reception of the satellite TV that can be seen fixed to the sides of homes. So we need three pieces of information which are needed to determine the look angles for the geostationary orbit. One is the Earth station latitude denoted by lambda e, and the next one is the Earth station longitude denoted by phi e, and the third one is longitude of the subsatellite point denoted by phi ss. So Earth station will receive the maximum signal level only if it is located directly under the satellite. Otherwise, it won't receive the maximum signal level, and that signal level decreases as the difference between the latitude and the longitude of the Earth station increases. So, based on the requirement, we can place the satellite in a particular orbit. Look angles are required at the antenna so that it points directly at the satellite. We need two angles of the Earth station antenna combined together are called look angles. One is azimuth angle and the second one is elevation angle. Generally, the values of these angles change for non-geostationary orbits, whereas the values of these angles don't change for geostationary orbits because the satellites present in geostationary orbit appear stationary with respect to Earth. Now let us define both the angles azimuth and elevation angles. Azimuth angle is the angle between the local horizontal plane and the plane passing through Earth station and the center of the Earth. And the angle between the vertical plane and line pointing to satellite is known as elevation angle. Vertical plane is nothing but the plane which is perpendicular to the horizontal plane, which you can see in this figure. This diagram shows the azimuth angle. So this is the azimuth angle, and elevation angle is the angle between the ground level and the line joining your satellite and antenna. So this is your elevation angle. And as I told already, the information which are needed to determine the look angles are lambda e, phi e and phi ss. That is Earth station latitude, Earth station longitude and the longitude of the subsatellite point. Latitudes north will be taken as positive angles and the latitude south will be taken as negative angles. Longitudes east meridian will be taken as positive, whereas the longitudes west will be taken as negative angles. Longitudes east of Greenwich meridian will be taken as positive. So for example, if a latitude of 40 degree S is specified, this will be taken as minus 40 degree. And if a longitude of 35 degree west is specified, this will be taken as minus 35 degree. So when calculating look angles for low Earth orbit satellites, it was necessary to take into account the variations in the Earth's radius. With the geostationary orbit, this variation has negligible effect on the look angles and the average radius of the Earth can be used. So denoting the average radius of the Earth, R is equal to 6,371 kilometer. The geometry involving these quantities, that is, for example, if ES denotes the position of the Earth station and SS is the subsatellite point, S is the satellite and D is the range from the Earth station to satellite, we have to determine the angle sigma, that is the angle to be determined. So in this diagram, there are two types of triangles involved in this geometry. One is the spherical triangle, which is shown in heavy outline, and the plane triangle, which is shown in this second diagram. Right. Considering the first spherical triangle, the sides of all arcs are great circles, and these sides are defined by the angles subtended by them at the center of the earth. Side A is the angle between the radius to North Pole and radius to subsatellite point, and it is seen that A is equal to 90 degree. A spherical triangle in which one side is 90 degree is called quadrantal triangle, and angle B is the angle between the radius to the earth station and the radius to the subsatellite point. Angle C is the angle between the radius to the earth station and radius to North Pole. So you can see from the diagram, C can be written as 90 degree minus lambda E. There are 6 angles in all defining the spherical triangle, and 3 angles A, capital B and C are the angles between the planes. Angle A is the angle between the plane containing C and the plane containing B, whereas angle B, capital B, is the angle between the plane containing C and the plane containing A. Okay, from this figure, you can note it down that capital B is equal to phi E minus phi SS. So the maximum value of B is here 81.3 degree. Angle C is the angle between the plane containing B and the plane containing A. To summarize this to this point, the information known about the spherical triangle is, we can write it as A is equal to 90 degree and C is equal to 90 degree minus lambda E, and B is equal to phi E minus phi SS. You can note that when earth station is west of the subsatellite point, B is negative. When east, B is positive. When the earth station latitude is north, C is less than 90 degree. When south, C is greater than 90 degree. And special rules known as Napier's rules can be used to solve the spherical triangle, and they can be modified here to take into account the signed angle B and lambda E. Only the result will be stated here. Now Napier's rule will give the angle B as angle B is equal to R cos of cos B into cos lambda E, and the angle A is given by R sine of sine B divided by sine small p. And these two values will satisfy this equation A and 180 degree minus A, and these must be determined by inspection by substituting and taking into account the values. Angle A is acute, that is less than 90 degree, and the azimuth angle AZ is equal to A. And I can see in the second diagram, angle capital A is acute, and the azimuth angle is inspection is given by AZ is equal to 360 minus A. In the third figure, that is in figure C, angle AC is obtuse and is given by AC is equal to 180 minus A, where A is the acute value which is obtained from the equation that is called capital A is equal to sine inverse of sine B by sine B, capital sine B by small sine B. Again by inspection, AZ is here AC minus 180 minus A. So angle AD is obtuse and is given by 180 minus A, where A is the acute value which is obtained by the same equation. By inspection, we can know that AZ is equal to 360 minus AD is equal to 180 plus A. In all cases, A is the acute angle returned by these equations. So, we can summarize all these terms as this single table, which is shown in here. So, for an angle of small a, lambda E will be less than 0, B will be less than 0, and AZ will be A. For B, lambda E will be less than 0, B is greater than 0, and AZ is 360 minus A. And for C, lambda E is greater than 0 and B is less than 0, and AZ is 180 degree minus A. And for d, small d, lambda a is greater than 0 and b is greater than 0 and a is at 180 plus c. So from these equations you can write small b as r cos of cos b into cos lambda e, which is given by 36.23. And capital A is equal to arc sine of sin b by sin b, which is 17.1 degree. So by inspection we can write that lambda e is greater than 0 and b is equal to 0, and then a is equal to 180 minus a, which is given by 162.9. Applying the cosine rule for planned triangles to the triangle, it allows the range d to be found to close approximation of that d is equal to square root of r squared plus agso squared minus 2r agso into cos b, where agso is the radius of the geostationary orbit. Applying the sine rule for plane triangles to the triangle of the second diagram B, and allows the angle of elevation to be found AL is equal to r cos of agso by d into sin b. So these look angles for KU band satellites are seen from the Thunder Bay, Canada, and you can see the preceding results not take into account in the case when the Earth station is on the equator. Obviously, a Earth station is directly under the satellite. The elevation is 90 degree and the azimuth is irrelevant. And the sub-satellite point is east of the equatorial Earth station, that is when b is less than 0, the azimuth is 90 degree, and when west, b is greater than 0 and the azimuth is 270 degree. So also the range as determined by this equation is approximate, and where more accurate results are required, for example, where propagation times need to be known accurately, the range is determined by measurement. For a typical home installation, practical adjustments will be made to align the antenna to a known satellite for a maximum signal. Thus, the look angles need to be determined with great precision, but are calculated to give the expected values for the satellites, the longitude of which is very close to the Earth station longitude. In some cases, especially with direct broadcast satellites, the home antenna is aligned in one particular cluster of satellites and no further adjustment are necessary. Thank you.